6.4 Inverting a 2x2 matrix. Now you can find the inverse of any non-singular matrix. You will recall that for a non-singular matrix, the determinant of that matrix doesn't equal 0. And that's what we see over here. Now the inverse of a matrix M is the matrix M to the power of -1, such that if we multiply the matrix M by the inverse of that matrix, this is equal to the identity matrix I. So I would represent the identity matrix. And you'll notice this is the same as the inverse of M multiplied by M. Now you may recall, an identity matrix is a square matrix in which the elements on the leading diagonal, starting top left, are all 1 and the remaining elements are 0. And identity matrices are denoted by IK, where K describes the size of the matrix. So if we have I3, that will tell us we have a 3x3 identity matrix. Along the leading diagonal we have 1s. The rest of the elements are 0. Now we have this formula to help us find the inverse of a 2x2 matrix. So if we've got the matrix M with elements A, B, C and D, the inverse of that matrix, that's equal to 1 over the determinant of M multiplied by this matrix D minus B minus C A. And what you can see over here is the A has been swapped with the D and the D has been swapped with the A. So we swap these two elements, and where we have the CB, we stick a minus sign in front of those. So the inverse of M, that's equal to 1 over the determinant of M multiplied by the matrix D minus B minus C A. And you'll note over here, if the determinant of M is equal to 0, in other words, if we have a singular matrix, you will not be able to find the inverse matrix. So for singular matrices, we don't have an inverse. And that's because for a singular matrix, the determinant of that matrix is equal to 0. So when we come to work out 1 over the determinant of that matrix, we'd have 1 divided by 0, which is undefined. Example number 14, we've got 3 matrices A, B and C. A has elements 3, 2, minus 1, 1. B has elements 2, 1, 2, 1. And C has elements 1, 3, 2, 0. And for each of these matrices A, B and C, we have to determine whether or not the matrix is singular. And if the matrix is non-singular, we have to find its inverse, and that makes sense. If the matrix is non-singular, we can find its inverse. If the matrix is singular, we can't find the inverse. So if we consider finding the determinant of matrix A, using this formula, we first of all have to find the determinant of A. So we begin with matrix A, which is equal to 3, 2, minus 1, 1. Then we need to find the determinant of that matrix. For a 2x2 matrix, you'll recall to find the determinant, we do A times by D minus B times by C. So finding the determinant of A, we're finding the determinant of 3, 2, minus 1, 1. And working this out, we have 3 times by 1 minus 2 times by minus 1. We have here 3 plus 2, which is 5. And because this does not equal 0, We can therefore conclude A is non-singular and therefore A has an inverse. And to find the inverse of this matrix, using what we discussed over here, we have 1 over the determinant. So we have 1 over the determinant, which is 5. And then with this matrix, we swap these. So we have 1 and 3. And then we multiply these by -1. So -1 times -1, that's 1. 2 times -1, that will be -2. And if you want, you can multiply the 1/5 into the bracket. So we have 0.2 minus 0.4, 0.2, 0.6. Now, if we take a look at the matrix B, we know matrix B is equal to 2, 1, 2, 1. The determinant of B, we're finding the determinant of 2, 1, 2, 1. So working this out, we have 2 times by 1 minus 2 times by 1. 2 minus 2, that's 0. We can therefore conclude B is singular and therefore B does not have an inverse. And that is in line with what we discussed over here. Now for matrix C, we know that matrix C is equal to 1, 3, 2, 0. So we now need to find the determinant of C. So we need to find the determinant of 1, 3, 2, 0. So working this out, we have 1 times by 0 minus 3 times by 2. It turns out here we get -6. And because this does not equal 0, we can therefore conclude C is non-singular and therefore C has an inverse. So to find the inverse of C, we have 1 over the determinant, so we have -1/6, and then we swap these two elements, so we have 0, 1, and then we multiply these elements by -1, so we have -2 here and -3 here. And if we expand the -1/6 into this bracket, we end up with 0, 1/2, 1/3, -1/6. Now with our results over here, we can confirm our results using the calculator. So if we enter into the matrix mode, let's define matrix A, 2 rows, 2 columns, that has elements 3, 2, -1, and 1. So if we were to find the inverse of that, let's load up matrix A, and then we press this button over here. And if we press equals, indeed, we get the matrix as shown over here. Now you'll notice, if we get matrix A loaded up, and if we press this button, so if you raise matrix A to the power of -1, you'll notice over here we get a syntax error. So whenever we find the inverse, we have to use this button over here instead of this button here. Now if we define matrix B to 2 rows, 2 columns, type in the elements, we have 2, 1, 2, 1. If we load up matrix B and raise this to the power of -1, you can see we get a math error. So B does not have an inverse. And if we define matrix C, 2 rows, 2 columns, type in that matrix 1, 3, 2, 0, load up matrix C, and then we will find the inverse of this. You can see the inverse is exactly the result we got here. So that's how we can use our calculator to check our answers. If A and B are non-singular matrices, in other words, the determinant of A and the determinant of B does not equal 0, then if we multiply the matrices A and B together and then take the inverse of the product of A and B, that's equal to the inverse of B multiplied by the inverse of A. For example number 15, we have to prove this result. We have P and Q, which are non-singular matrices, and we have to prove that the product of PQ inversed is equal to the inverse of Q times by the inverse of P. Now to do this question, we would have to use what we discussed previously. That is, if we have a matrix M, and if we multiply that by the inverse of M, that's the identity matrix. Alternatively, if we have the inverse of M and we multiply that by M, we'll still get the identity matrix. And multiplying a matrix by the identity matrix will just result in that matrix. It's pretty much the same as multiplying by 1. Now to do this, we will make a substitution. We will let the matrix C equal P times by Q inversed. So in other words, using this result over here, we can say that PQ multiplied by this matrix C will equal the identity matrix. And that makes sense. We have PQ, which corresponds to this M essentially, multiplied by C, which corresponds to the inverse of M, and multiplying these two together will give us I. So you can see here we get the result of I. Now our goal over here is to get C by itself, and if we get C by itself, then we've got C, which is the same as PQ multiplied together and then inversed. We'd have C equals something. Now we can't just divide I by PQ. It doesn't work like that. Instead, we'd have to take the inverse of matrices instead of dividing. So, if we have over here P multiplied by Q multiplied by C equals I, to get C by itself, we can first of all multiply both the left hand side and the right hand side by the inverse of P. Now why would we want to do that? Well, if we take a look at the inverse of P multiplied by P, this result is the same as the identity matrix. So we've got this result multiplied by Q multiplied by C. This is equal to the inverse of P multiplied by the inverse of multiplied by I. So here we get the identity matrix multiplied by Q multiplied by C. And this is equal to the inverse of P multiplied by the identity matrix. And multiplying a matrix by the identity matrix, that's the same as multiplying by 1 essentially. So I times Q times by C, that's just QC. And this is equal to the inverse of P. And remember, our goal is to get C by itself. Now we can't just divide by Q on both sides. Instead, to get the C by itself, we first of all have to take the inverse of Q on both sides. So we've got the inverse of Q multiplied by Q multiplied by C. This is equal to the inverse of Q multiplied by the inverse of P. Now why did we do this? Inverse of Q times by Q, that's just the identity matrix. Perhaps if we put this in a bracket, might make it a bit clearer. We've got the identity matrix multiplied by C. This is equal to inverse of Q times by inverse of P. Now of course, identity matrix multiplied by matrix, that's just that matrix, it's the same as multiplying by 1 essentially. So here IC, that's the same as C. And on this side we've got inverse of Q times by inverse of P. And knowing that C is equal to PQ multiplied together and then inversed, we can therefore conclude PQ inversed, which is what C is, as we said over here, this is equal to inverse of Q times inverse of P. And that's exactly what we wanted to show. Example number 16, we've got A and B which are non-singular 2 by 2 matrices such that B multiplied by A multiplied by B is equal to the identity matrix. And for part A we have to prove that A is equal to the inverse of B times by the inverse of B. Now if we begin over here, our goal is to get A by itself. So for part A, if we begin with B times by A times by B equals I, to get A by itself, we can't just divide both sides by B. Instead we'd have to take the inverse. The justification for that, inverse of B times by B, is the identity matrix. So if we inverse B and then multiply the inverse of B by the left hand side and the right hand side, we have inverse B times by B times by A times by B. This is equal to inverse B times by identity matrix. Inverse B times by B, that's the identity matrix. So we've got the identity matrix times by A times by B. This is equal to inverse of B times by identity matrix. Identity matrix times any matrix is that matrix. I times by A, that's just A. So we've got A times by B on the left hand side, and on the right hand side, inverse of B times identity matrix, that's just inverse B. It's essentially the same as multiplying by 1. Now again, our goal over here is to get A by itself. We can't just divide both sides by B. Instead we'd have to take the inverse of B on both sides. So we've got A multiplied by B multiplied by the inverse of B. This is equal to the inverse of B, which is what we've got already, multiplied by the inverse of B. The reason I want to do that, you'll notice here, B times inverse of B, that's I. So we've got A multiplied by I. This is equal to inverse B times inverse B. So A times by identity, that's just identity, sorry, that's just A. So we can therefore conclude A is equal to inverse B times inverse B. So therefore, we've proved the result. Now for part B, given that the matrix B is equal to 2, 5, 1, 3, our goal over here is to find the matrix A such that BAB is equal to I. Well, of course, we can find the matrix A by first of all finding the inverse of B and then multiplying the inverse B by inverse B. For us to find the inverse of B, we first of all need to find the determinant of B. So the determinant of B, that's the determinant of 2, 5, 1, 3. So we have 2 times by 3 minus 5 times by 1. It turns out here the inverse of B is 1. So to find the determinant of B is equal to 1. So to find the inverse of B, that's equal to 1 over the determinant of B. So we have 1 over 1. And we multiply this by the matrix over here. We take a look at our original matrix. We swap these two elements. So we have 3 here, 2 here. We multiply these elements by minus 1. So we've got minus 1 here, minus 5 here. So the inverse of B, that's equal to 3 minus 5 minus 1, 2. Now, on our calculator, we can confirm that result. If we go to the matrix mode, define this matrix, we've got 2 rows and 2 columns, type in this original matrix, we've got elements 2, 5, 1, 3. To find the inverse of that, let's load up that matrix which we've just defined. We wish to take the inverse of this. Indeed, we get 3 minus 5 minus 1, 2. So now, to find out what A is equal to inverse B times inverse B. So we will multiply over here 3 minus 5 minus 1, 2 by 3 minus 5 minus 1, 2. Now, to multiply these matrices together, we go across this first row, down this second column. And the resulting matrix will be a 2 by 2. So for this element here, we've got 3 times by 3, and then we have minus 5 times by minus 1. For this element here, we go across, down this column, so we've got 3 times by minus 5, plus minus 5 times by 2. For this element here, we go across, down, so we have minus 1 times by 3, plus 2 times by minus 1. For this element here, we go across, then down, so we've got minus 1 times by 5, plus 2 times by 2. This is the resulting matrix which we wish to work out. So if we tidy all this up, 9 plus 5, that's 14. Minus 15 minus 10, that's minus 25. Minus 3 minus 2, that's minus 5. Minus 5 plus 4, that's 9. So the inverse of it, the matrix A is equal to 14 minus 25 minus 5, 9. Now you'll notice over here, this is stored into matrix answer. So if we load up that matrix answer, and then if we multiply this by matrix answer, so we're multiplying inverse of B times inverse of B, You can see here we get 14 minus 25 minus 5 and 9. So that will be a good way of showing you're working.